The next problem which we have is a pretty interesting problem of chemical equilibrium. We are given that 0.15 moles of carbon monoxide taken in a 2.5 liter flask is maintained along with a catalyst at 750 Kelvin, so that the equilibrium reaction carbon monoxide plus hydrogen reacting to give methanol can take place. In this reaction, hydrogen gas is introduced until the total pressure of the system becomes 8.5 atmosphere and 0.08 moles of methanol is formed at equilibrium. We need to find the Kp for the reaction, the Kc for the reaction, and the final pressure if the same amount of carbon monoxide and hydrogen are taken in the flask but there is no catalyst present. So getting started with this problem, at equilibrium we have temperature is equal to 750 Kelvin, we have a total pressure of 8.5 atmosphere given, and we have the volume of flask to be equal to 2.5 liters. Since all the gases involved, assuming them to be ideal gases, we can apply the ideal gas equation. PV is equal to nRT. Here N represents the total number of moles present at equilibrium. On substituting P to be equal to 8.5 into 2.5 is equal to N. The value of gas constant is 0.0821 and temperature is 750 Kelvin. We get the value of total number of moles to be equal to 0.08. I am sorry, after solving for this equation, we get the value of N to be equal to 0.3451. It was not 0.8, it is 0.3451. Now we will write the reaction. The reaction is CO2 plus 2H2 gives CH3OH. The initial number of moles of carbon dioxide is given to be equal to 0.15. Let the initial number of moles of hydrogen to be equal to A. At equilibrium, let X moles of CO2 are getting consumed. So 2X moles of hydrogen will get consumed to give X moles of CH3OH. And we know that since it is given in the problem, 0.08 moles of CH3OH will be formed at equilibrium. So the value of X will be equal to 0.08. Also we know that the total number of moles present at equilibrium is equal to 0.5 minus X plus A minus 2X plus X, which is equal to 0.5 plus A minus 2X, which is equal to 0.16, and this is equal to total number of moles present at equilibrium, which we calculated from the ideal gas equation. So this becomes A minus 0.01 is equal to 0.3451, and hence the value of A comes out to be equal to 0.3551. Note that this A is the initial number of moles of hydrogen present. Now the value of Kc can be very easily written as the concentration of methanol at equilibrium, which is equal to X, that is 0.08, divided by the equilibrium concentration of CO2, which is 0.5 minus X, that is 0.07, or rather it was the number of moles of CH3OH present at equilibrium, so we have to divide it by the volume of the flask. Always remember that in the formula of Kc we have the concentrations of the reactants and products and not the number of moles. Hence we have to divide the number of moles by the total volume of the flask, which was 2.5. Here the concentration of CO2 is not 0.07, it is 0.07 divided by 2.5. And the hydrogen concentration, which is equal to A minus 2X, that is 0.3551 minus 2X, which is 0.16, but this is the number of moles of hydrogen present at equilibrium. We have to divide this by 2.5. This becomes 0.1955 divided by 2.5. On solving this thing, we get the value of Kc to be equal to 186.88. Also we know that for a gaseous reaction, Kp is equal to Kc into RT part delta N. Here we know the value of Kc to be equal to 186.88. The value of R is 0.0821. The value of temperature is 750 Kelvin, and delta N is the sum of stoichiometric coefficients of products minus the sum of stoichiometric coefficients of reactants. Here it was CO plus 2H2, so 1 plus 2 equals 3, and here we have 1, so delta N is equal to 1 minus 3, that is minus 2. Hence our value of Kp becomes 186.88 into 0.0821 into 750 raised to the power minus 2, which gives the value of Kp to be equal to 0.0494. So our answer for the first part is the value of Kc is 186.88 and the value of Kp is 0.0494. In the second part, we are given that the same amounts of carbon monoxide and hydrogen are taken in the flask, but there is a slight change. There is no catalyst involved in this part. What was the role of catalyst? It was causing this reaction to take place, and hence if no catalyst is present, then this reaction will not take place, methanol will not be formed, and hence the total number of moles present at equilibrium will be equal to the initial number of moles of carbon monoxide present and the initial moles of hydrogen initially present. Moles of carbon monoxide initially present were given to be equal to 0.15, and the initial number of moles of hydrogen, that is the value of A which we found out, was 0.3551, and hence the total number of moles present becomes equal to 0.5055. These are the total number of moles of the gases present at equilibrium if no catalyst is involved. Now we want to find the total pressure at equilibrium if no catalyst is involved. So we can use the ideal gas equation of PV is equal to nRT, P into the total volume of the flask, which is 2.5, is equal to total number of gaseous moles present at equilibrium, which is 0.5055, into gas constant, which is 0.0821, into temperature, which is 750 Kelvin. On solving this equation, we get the final pressure as 12.45 atmospheric pressure. Hence our final answers are Kc is 186.88, our value of Kp is 0.0494, and our final pressure at equilibrium if no catalyst is involved in the reaction is 12.45 atmospheric pressures.